Okay, Assalamu alaikum. Good afternoon. It's a pleasure to meet you again here. Today's session is how to understand a very complex Pytorch code. For now, I think most of the codes you already encountered are actually very simple. So maybe from the beginning of the next week, you will start to observe some a bit harder notebooks. So in this session, I picked two codes, okay, with data types you have never encountered before, with problems you have never encountered before, with a very complicated Pytorch. Okay, why? So the question is, can we understand this complex code in half an hour? It's a good question. Okay, so the whole goal of this session is if I give you a new total code with new loss, new observation, new everything, can you understand it? Okay, hopefully by the end of this session you will say yes. Okay, so if you got this code is now about something called WebNet. What is this? I don't know. In Pytorch. And what is emo? I don't know. But this is for train, okay? I just picked it from some random competition. Okay. So you have this code and it includes all this stuff. How to start reading this code? Annie? No. Hmm? Maybe if you want, but no. For me, no. Actually, don't stop like that. No. No, that and like this only this. Oh, okay, how it started. For me, I think the best start is directly to go to the forward in the model. Skip anything, just go directly to the forward. Yani, mashallah, show this is the class of the model. We have this block, have this block, this block, this block, and you have the forward here. So the best place to start any Pytorch code is from the forward of the model class. I guess that's the best option. Then from here, we will expand until maybe cover all the code, okay? So do you understand something here? Yes, that's expected because it's a total new code, yani. But let's try to make sense, yani, each step. Firstly, yani, what does the forward actually does? It actually pick an X in the training loop, yani. We give it an X, it's substituted here, and it gives us this output, okay? Yani in Pytorch generally, okay? We have the forward in the model class, we pick an X, input it into the model, it will directly go to the forward, it will pass through all the layers, and we get some output that we define actually, okay? Then we return it. After return it, we calculate the loss, we do this stuff, right? Anyone clear? This is clear, right? It's easy Python, okay? So let's start. First, here it says that the X shape is actually BL input channels. I think this is a bit new. What do you have in the tabular data? No, the bad side, the shape. Sorry? No, the shape you have tabular data. It's two things. Yeah, samples and features. Okay, it's called rows of columns. Or when you do that in Pytorch, we usually call it batch size and features. Okay. So what about that image? Give me the full shape. Batch size, channel, height, and width. So you have four components, right? In table data, you have two components. So here, see three. Okay, so this might be a bit new. But you can see the channels out there, right? So what if I put the channels here? We have batch size, channels, and something, right? Sorry? Not an image. If it's an image, we have batch size, channels, height, and width. But this is three. Okay? In image, we have batch size, channel, height, and width. In waves or sequences, we have batch size, channels, height. Okay? In 3D image, we have batch size, channels, height, width, and depth. It depends on the last three elements. If there are three, this is a 3D image. Two, this is 2D image. One, this is 1D image, which is a wave. So here we are dealing with waves. Okay? Actually, these explanations you hear them from me now. Okay? But if you were alone, you are just got this code and want to understand it, you have ChatGPT. Yeah, utilize it well, yeah. Okay? So he says here that we have an input like this, batch size L. I don't know what it says exactly. but here it is the length. When we talk about the waves, we talk about batch size, length of this wave, and channel. When we talk about text, we talk about the batch size, the number of words, and the channels. You can interpret the channels as features, okay? From here on. When you see channels, this is most likely will be features, okay? So it's like we have batch size, we have the length of this wave, or the number of words in this text, and we have the features that represent each second, for example, if it's a wave. Yeah. If it's a wave for 60 seconds, it means that for each one of these 6 seconds, we have, for example, 30 features. Makes sense, right? So he just picked this and input it in something called WaveNet1. Okay. And notice the same X, he input it into something called WaveNet2. Okay, but change something here. Change something here. Okay. Try to just consider everything here as a black box. This is how you begin understanding any architecture. Consider everything here in the forward as black boxes. And just try to interpret firstly the inputs. Okay, so here we knew we have this shape, weird shape, okay? And in X, he just picked something and passed it here. And in here we get X1. Okay? He picked this X1 into some average pooling, and we got X1, right? Right? Here he picked X, so he didn't change this again. So this is the first step. It's like he took X, pass it through 2 layers, and keep it there. Okay. Then he took another part of X. Okay. Got X2, passed X2 to average pooling, and got X2 here. So it's like he separated the input into 2 parts, right? Passed the first layers and got X1, the WaveNet2 and the average pooling got X2. So next he did what? Concatenate X1 and X2. Oh, so it's like we are extracting features from here, then we are concatenating them together, right? Makes sense. Why did he split it into 2 parts? That directly tells you that this part of the data and this part of the data are different. So they are handled differently, okay? So then he just picked two features, used concatenate, and wrote x is equal 1. I return to dimension, but for now, assume he just concatenated 2 features, 2 different types of features, okay? Then we have head. What does head usually mean? The classifier, okay? So basically, he took the features we extracted, passed it to the first head, and picked the same features, passed it to the second head. So we have 2 heads. What does that tell you about the target? We have 2 targets, okay? It means that, if you can imagine the architecture, we have now the same X, we split it into 2 parts. The first part, we processed it differently. The second part processed differently. Then we concatenated the features, then used these features to predict 2 targets, right? Easy. And just return these targets. So for now, you just understand the model as a black box. Okay, so this is the first step. Let's now try to interpret the data. Here, he says, pick all the P's, the batch size, and all the samples, okay? And all the length, all the seconds, for example, but pick channels from
1 to 4.
Yeah, from 0 to 3, 0, 1, 2. So we have 3 channels. Okay, yeah. And here, he picked from the 3rd channel until the end. So how many channels do we have in this data? That tells you we have more than 3 channels, okay? That tells a lot about the data. So it's like the first 3 channels represent something, and the rest of the channels represent something else, okay? So if you now went to the competition data, and tried to read the data, you will find these waves represent something, and this wave represents something. That's why he separated it here, okay? Then he concatenated it based on axis 1. What does axis 1 mean here? Why not axis 0? Why not axis 2?
Axis 1 is the column.
Which column?
The
Which column here? We are talking about x.
I think it's one way we're measuring the length. We are measuring axis 1 is the length. We are measuring the
Have a look again.
based on the column. We are measuring the x1 and x2 based on column.
Which columns exactly? In data frames, we have axis equal 0 rows, we have axis equal 1 columns. But in Tosh, we talk about the dimensions. Maybe we have 4 or 5 dimensions. Okay?
I think it's the
nodes, you concatenated them along the length.
The
So
length.
he wants to get back because he separated the length before. Now he wants to put them back together, and the batch size is the same for both of them. So he didn't.
So you are saying that we extended the length. So if the first one is 60 seconds, and the second one is 60 as well, we have 120. The answer is incorrect.
Measure them based on the channel.
Have a look what does the WaveNet output here.
That's it. Based on the
Yeah.
channel.
If you look here, it tells you that WaveNet, yeah, it takes the input channels at the end, but it returns the features here and the length at the end. So, and the WaveNet 2 as well do the same, okay? And notice how average polling removes the L, so it averages all the seconds. You see? So it's like we have a 60 second voice, for example, and we want to classify, for example, whether this sound is for, I don't know, any classes, okay? So it's like we want to look into the voice as a whole, not as individual seconds, okay? So that's why like we average all the seconds together to get a representation for the whole voice instead of 1 second. Make sense?
Yeah.
Okay. So he put it like this, and the other one like this. I concatenate across the one. It means across the features. This is the features. As I mentioned, when you see in channels, you can interpret them as features. Okay. So it's like it's like this WaveNet captured different features than this one. Okay. And then we concatenate them together so the model could see later both types of features. Makes sense, right? And yeah, just pass these features to the first head, second head, and get the output.
But he concatenated them. So it's like
they got half. For now, we are not talking about how we just transform this into this. We consider the WaveNet as a black box. Okay, we are just saying if we have a block like this and it converts the shape like this, does this as a black box? Does this make sense for you? The forward?
As a black box, huh?
Yeah.
Yeah, it makes sense.
Yeah, but we take it go into details. Okay, so I just start by this. Okay, because it first let you what all this notebook about. Okay, so here we just looked into this. We don't know what the data is about also already. And I did tell you about what actually the competition actually even compute or calculate. I just went into a random piece of code, okay, and you managed to understand it. Okay, so this is the first step. Now the second step is that we try to decipher each block. Okay, so we'll go to the WaveNet 1 and WaveNet 2. So they are defined self.wavenet. So where you will go?
What?
Yeah, in the minute model class. It's this one, right? So here we have WaveNet 1, WaveNet 2, and he says, oh, we have here 3 channels and here 4 channels. So maybe now you can interpret why we separated these two here, right? Makes sense, right? So consider now the WaveNet as a black box like this, and let's go to the other layers. It's like you're going step by step. Okay, we are not now directly going to the details of WaveNet, but the new information we know now that it gives here 3 channels and here we have 4 channels. So let's go to the next part of this, this forward. We have the global average pooling. Let's say what, notice that it's the same here and here, the same function. So it's adaptive average 1 pooling 1D. 1D means we have 2D, right, in CNN. 1D in 1D CNN, simply. So it's like, it just average all the length. So instead of considering separate seconds in the voice, for example, you are seeing it as a whole, okay? Why do we do that?
We don't want to go second by second.
لا, it's okay من الناحية دي, but why do we need to change the shape like this?
The voice should be 1D.
No, I understand. Think about the next step.
So that we can split.
Not screen, but we want to put them into samples and features. It's the same concept as before. Do you remember in the CNN, we extract feature in byte size, channels, height, and width, and we do flatten? Yeah, here we extract features. In originally, it's the byte size, length, and channels. And we extract and we flatten them. You can consider pooling as some sort of flattening. That's why we, at the end, use the head, the classifier. Do you remember the classifier? Use samples of features. So it's the same concept as before, right? Makes sense, right?
Oh,
So,
I have a question.
yeah.
In the Y, but we can't miss. The feature size will be B and 128, right?
Yeah.
The steps after to it take the Y as a parameter,
Yeah.
but both deals with 64 only.
I think this is a mistake. I think this is a mistake. You're correct. It should be 128 because we are concatenating from 64 plus 64. It will be 128. And yeah, it's a mistake from the one who wrote that up. Okay. Well done. Okay, let's see the next layer. We already know the first four. The concatenate is already easy. We have the two heads. So here we have head one. It's just like a simple linear, right?
Yeah.
And this one as well as simple linear, right? What's the difference between the two? Yeah, number of classes. So this looks like a binary classification. Okay, and this looks like multi-class classification. So actually the problem originally, and this whole problem, is that you have sensor just attached to your hand, okay, and you are making gestures using your hand, okay. First, I think you should classify whether there is a gesture or not, and this is here the binary classification, okay. If there's gesture, okay, classify it into one of 5 classes, and this is the second head, okay. So you are optimizing them together, right? Easy, makes sense. So now you understand the model class somehow, yeah. Actually, if you want to use such a notebook, mostly such special defined models, and like the WaveNet, actually, it turns out that you don't have to understand everything in the code in order to use the code. Okay, from here on, you can actually take this fact from me. Yeah, WaveNet here, we can use it, but we don't exactly know how it works. But if you want to look, have a look. Yani for now, if you want to use the whole code, you will just use this. You know how to input the WaveNet, and you know how to get the output of this WaveNet. You know how the shape changes here, okay? And so you can use the code. So now we reach a state where we weren't understanding anything about the code. We just look into the forward, the custom model, and we can now understand how the flow goes from beginning to end, okay?
Channel something of a hyperparameter, or we
I know it depends on the data. Yeah, there in the data itself, they provided several channels, okay? And they mentioned in the data itself that the first 3 channels represent something, and the fourth represents something else. So that's why here we consider them separately, okay? But maybe if you have 7 channels as a whole, maybe you can use only one WaveNet if they all are the same, okay? But notice how he handled them differently, but we can actually define one and put 7 and try, okay? If we got better results, then it makes sense and it's good. Okay, otherwise, maybe we'll refer to this. But usually, the decisions of how you define your splitting, how to define your model, requires some domain knowledge. So you differentiate if there are different types of data types or something. Okay. So maybe we can have quick look into the WaveNet. You are not supposed to understand this, I guess. But here's the WaveNet. If you want to understand the WaveNet, you will go to the forward. Yeah, the forward. Okay, so here, have a look. In the forward, he actually take the original data we saw before. He used permute. So he put the channels at the beginning, right? And it's like batch size, channels, height, and width, but we have no idea, right? And he just passed this to the model. We got the output, and this is the output we saw before. Okay, make sense?
Can you explain the arrow mark?
The
arrow mark. In a forward line. Just forward line.
Tensor.
Yes.
Here?
No.
Harry? It's not important. It just tells you in Python that the output of this function, it will be tensor. You don't have to define it. It's just Python syntax. Yeah. Okay. But now, if you understand the forward, you can use the, but the fact you have to know that if you understand the forward, you can use the model, okay? So basically here, he just put the channels at the beginning because all Pytorch actually requires the channels at the beginning, then pass it to the model, some model, and it actually gives you the output that we saw before. So we can use this block now, right? Yeah. So let's go a bit into details. We have something called model. Let's see how he defined it, okay? It defined as sequential. It's like we have different layers. Layers sequential. We just defined them previously that separately. But you can use something called n sequential and define the blocks like this. Makes sense for everyone? Okay. So we have something called wave block. It gets input channels, and oh, this is the output features like the CNN, right?
Yeah,
32, 32, 64, 64. You remember, right?
yeah.
So it makes a bit of sense now. Okay. But here, the only difference is that instead of dealing with 2D, we are dealing with 1D. So given it makes sense, let's look into detail of wave block itself. Plus, where is wave block? Wave block, wave block. Come on, please. Please. Anyway, we have the wave block here. Okay. So to understand this, we will go to the forward. Okay, here's the forward. Okay, things started to get a bit complicated, maybe. We have something called comms. Comms maybe is an abbreviation for. Okay, so let's see what comms here is. And oh, self.comms, conf 1D. Okay, this makes sense, right? We have conf 2D before, and this is 1D. So it's like it takes several conf 1D. I don't know what does it do here, yani. Like in number of rates is like I think the L, if I'm not mistaken, is the L should be. Anyway, I think you see it get complicated here, right? What you see here now is basically the implementation of something called WebNet. Okay. In order to understand this part, you have to understand its theory. Okay, when you understand its theory, it will make sense. It's like when you see the implementation of the variation rate autoencoder. Makes sense, right? But now you can see a lot of tan H sigmoid and I don't know some random stuff, yani. But for now, to use this model, you don't have to understand this. You already know how to input it, you know how to output it, and generally you know how it works. It's to use some conf1d. Okay, you can see conf1d, some kernel side. It makes a lot of sense now. It's like it just have some wave and it processes somehow using conf1d. Okay, that's all the node we need from this. It's WaveNet. Okay, we use a blocks of this WaveNet into this architecture. Okay, we just pass the wave into this model. We got output. We use this WaveNet twice, one for 3 channels, one for 4 channels. Extract features from each one separately, concatenate the features, and calculate 2 targets and return the output. Easy, right? يعني والله هو انت مثل ما قلت it's not always necessary to understand everything because you will very likely يعني be able to understand what you will work with a lot. يعني if you work with something quite a lot, yeah, this thing maybe you will understand. You have to understand it well. You have to understand the theory and this stuff. But mostly, when you encounter new problems, okay, firstly try to consider them as black box. To try to make a full baseline. And يعني for now we don't have to understand more about this architecture to use it. Okay, for now we have very good understanding and we can manipulate this forward well. Okay, we can manipulate the features, for example, or manipulate the channels. We can debug if we have a code, a problem here. We at least understand how it works, so we can debug it. Okay, so that's actually all you need to use it.
How do I know what follow the stuff?
Check just what he defines the model is. Okay, so you notice he defined it as a custom model. So you'll just go to this one. Okay, makes sense. So yeah, that's it. You don't have to understand a lot of the details in order to use the network or to understand the whole notebook. Okay, so we know that we have the model and we return some batch size and the classes. So it's binary classification and multi-class classification. So we understand the forward. What's the next step? Where do you go? Huh?
I have a question.
Yeah.
Can we go to the
Wave block, yeah. Wave block. This one?
Yes. No, it's in the
Forward?
Yes. We have input and then output features and then a number.
Here?
In the wave.
This is the forward of the wave block.
The forward of the wave.
WaveNet. This one?
Yes.
Yeah.
We have the input features, input channels, then output, and then a number 12, 8, 4, 1.
12,
in the first wave block, it is 12.
Here. It's like the CNN. What do you do in the CNN? So you put here the number of channels, RGB or one, right? And this is the out features. Yeah, the same. This is the input features.
And then what is the 12? After that?
I think it's the stride, if I'm not mistaken. We have stride, we have kernel size, we have padding. This all exists in, yeah, the same. Okay. You can just refer to the documentation to know which value and refers to which. Okay. So it makes sense, right? So what's the next step after the forward, after understand the model? What's the next step? Yeah, the dataset class. Go to the get item in the dataset class. Okay, this is the custom data. I just want to go here. And it's mashallah very simple. Yeah. Okay. So it's like just it has some indices in Texas. It's like we are dealing about sequences. We are dealing about something called X, about something called Y hard. What is this? Let's go to the init. Okay. He defines him there as indices or indexes at df.sequenceid.unique. What does that tell you? Not exactly. It's a bit of more complicated data. But what does unique firstly do, Yan? Yeah, it moves the repetition. So that tells you firstly, we have sequence ID, a column called sequence ID in the data, and it's repeated. Okay. So we did this to remove repetition. So it's like we want to consider each sequence only once. And each sequence has a lot of samples. So just wait a minute. Each sequence has a lot of samples. What does this tell you about the type of the data, representation of the data? No, it tells you that it is a wave. Sequence that have many data. Many data means each one could be a second. Okay, so that's why we consider each sequence once, because later we have the L as one of the in the shape, right? So it's like we will put each piece of sequence as a whole. We will consider this only once. Makes sense, right?
Each sequence is a wave, right?
Yeah, it's a wave. Each sequence ID is a wave. So maybe have 1,000 samples.
So we want only the unique one, which is...
We want the unique names, so we consider all this as one block. Right? Make sense? So yeah, he just took the uniques here. He just picked one of them here. And x equals self.x.index. This means x is like the data frame or the data frame of the data, right? Let's search for this x. Self.x, define here, self.x, x is passed as x. So where is x? X is passed in the init, right? In the data, custom data, right? Let's go to see where custom data has been used. Here. So, it's the df train, right? Or the second one. It's all x. Okay? It's all the features. Let's go to all x. I hope you are seeing the point, is that we are starting from something and we keep expanding. Okay, so if you just expand it similar to this way until maybe you finish, you'll find yourself actually passed all the code and you understand it. Okay, so this is, I searched for all x and here it is. He just defined all x here as an empty list. He went to the df train, the data frame, went to the sequence ID and went to unique, put unique. So he wants to consider also his sequence once, right? He picked all the samples from this data set that has the sequence ID equal to this one. So this might have, for example, 1,000 samples. This, the samples for this sequence, right?
Yeah.
So later, the next step, I think he picked the features. Emo calls, I think, are the features. Okay, and he just put them as x. So x represents the features. Okay. He put values to convert. He put values to convert to NumPy. Okay, because we usually like NumPy. There's something called bad or truncate. It's just pre-processing. When we have a wave, it should be in a fixed length. Okay, so it's like when you have text and you deal with NLP and something, maybe you have 500 words, right? And maybe in another text you have only 200 words. Okay, so the model cannot deal with different sizes. So you have to either truncate them, so put all of them as 200. Okay, or pad them, make all of them as 500. And if there is something, some essay or text that is less than 500, just put bad, something called padding. Okay, it's like a placeholder. Yeah, exactly. It's fine. It's just to make a fixed length. Okay, that's why he do it here, because we have a way that he tells you about this. So he picks the target and put it aside. Okay, he picks something else sequence type and put it aside as y hard. Okay. For now, maybe you have to understand it. You have to go to the data, but this one is I guess this is the binary target, and this is the multi-class target. Okay, that's why I have two targets. And he just concatenated the data. Notice how he standard scale x from 0 to 3, x from 3 to... Does mean? Yeah, exactly. You see it. You remember it from below, right? The same channels. So it tells you that he actually standard scale this one, but he didn't do it to this one. Okay, maybe because of domain knowledge, and he knows that this should be standard scaled and this not. Okay, so he concatenated this as features in the columns. Okay, and if there are any nans, and I guess replace them with 0. Yeah, fill the nan with zeros. Put this as x are features, y as the first target, y hard as the second target. Put it as array. Nice. Now let's return to where we came from. We said custom dataset, replace here all x, all y, right? And you have the df. And all y hard. This is the first target, this is the second target, and this is the features. So in the get item, let's return to get the data here. Substitute them here, x, y hard. Get to the x here, x, y hard. We get here. So basically, choose one sequence, okay? Choose samples of this sequence, sample of target, these two targets, and just return them intensive. Make sense? Now we understand the custom dataset. So where to go next?
training loop.
training loader ما easy هي واحدة هو سطر واحد. No. The train loop. Okay, let's go to the train loop.
Training loop.
So let's go to the train loop. This is train evoke. Okay. So what is the input? Train loader, model, optimizer, evoke, scheduler, device, right? Let's before going into, let's look at this. Okay. So firstly, search where is train evoke used. Where is used? Where is it used? Yeah, in the final loop, the evoke loop, right? Let's go to the evoke loops. This one. So before going to the details, let's just go and just use what we came for. Where is the train loop? Here's the train book. Let's use train loader, model, optimizer, evoke, scheduler, and device. Let's have firstly a look at the train loader. Where is the train loader? Yeah, here's the train loader. Very simple. We pass the dataset. Okay. So basically, we define the dataset. Let's go to the dataset. Here it is. We define the custom dataset. Config train fault x train y x valid y valid y hard valid. So train and validation, right? So let's return to these. Okay, let's go up. We have the train faults, for example. For the train fault, let's see the x train y train. Here he have x train y valid. He went to the features and pick the samples for train. Went to the features and pick the sample for valid. Assign them to train and valid. Okay. The same goes for the target. You have y target, y train, y valid. And the same goes for the second target, right? Make sense? Okay, let's go up. We have train index here. Where did we get that from? Okay, so train index, we have train index and valid index. It's like pick all, yani MP where, it's mean find wherever the sequences yani we are using equal specific item. Just we have a loop here. Do you understand that? Yani, less comprehension. It's like we have a loop. It's a loop, okay, but it's written yeah, in some short idea. Okay, so it's like it go into a loop of the train sequences, and it's like pick all the loop, pick all the samples where this sequence exists here. Yani. It's like exists here. Okay, and here pick all the samples or pick all the index yani, or dice of the samples where yani, they exist in the valid. Okay, so that's why how we get train index and valid. Let's see the train sequence and valid sequence. Let's go up. Here we have train sequence. It's coming from train false, and this one coming from valid false. Okay, so let's go up. Let's go to train the false and valid false. It's here. Okay, so it's like, wait a minute. We return to the first data frame we have ever. Okay, from this data frame, it tells you that if fold doesn't equal fold, and here fold equal fold, what is the split use here? It's k-fold. Does this make sense for you for k-fold? Try to substitute the number in the fold. What you'll get? It does make sense, right? Yeah, it's like if yeah, exactly. If I have the fourth fold, for example, okay, pick all the validation folds as this fourth fold, and for the rest, pick them as string. Makes sense, right? So
it's like the top that happens to pick by.
yeah, exactly. That's how we fold. And actually we get the false from here, right? From this run loop. So how do you think we will use this train loop below? We will have a loop for I in range 5, A or K, okay? So we'll use substitute this here. Let's go to that loop. Here, type for fold in 0, 1, 2, 3, 4. Substitute the fold, and you will get the predictions, and regardless of how this goes. But this makes sense, right?
Yeah.
Yeah, it makes sense. So where did you get this fold from? I mean, just a second. Here, you can see that we already have fold assigned to the data frame, right? Yeah, it's assigned to the data frame. So let's go up to see how this has been split. Where is the validation? Here. Okay, stratified group K fold. Number of splits equals something. And you use a loop here, and you assign the number of fold to the data frame. Makes sense? This makes sense. And aside from the details, but it makes sense, right?
So it will be none for all of them instead of 4 rows.
It will be?
It will be none for column fold and the whole that frame,
Yeah.
except 4 rows. Or 5 rows. 0, 1, 2, 3, 4, 5.
I don't understand that.
The whole data frame has a new column called 4.
Yeah, it's empty.
Yeah, it's empty now.
Yeah, we are filling it.
Yeah, except 5 rows.
Except 5 folds?
5 rows, Rob.
Why 5 rows?
Because we add them.
How do we add them? It's not, no, it's, firstly, we have something called fold and it's empty. What is the whole, the final goal? The final goal is maybe I have a data set of 10,000 samples, okay? Maybe for the first 2,000, we will put back 1 for all of them. For the second 2,000, we put 2 for all of them. Makes sense, right? It begins with 0, but it's okay, okay? Makes sense here, right? Regardless of how we use this, yeah, you can forget that. But yeah, we assign the fault, so we managed to split the data and put the split into the DF train, right? Right?
The DF train has 0 to 4.
Yeah, exactly. And here it tells you how many number of samples we have in each one. We have 115,000 يعني. So the data is around 500,000 samples. Okay? So if it makes sense, let's return to where we came from. We came, I guess, from the train loop here. So we understand how this goes, right? Okay, we got all the sequences split into train and validation because we have train faults and validation faults. Make sense, right? And we picked the indices for them. We splitted the features and charges based on them. We defined the custom dataset based on them. Okay? You can forget this. This is for debugging. And if I'm debugging, just use 2 ebooks. And just for not necessarily. But we pass these datasets into the data loaders. Make sense? Right? Bus size, shuffle, number of workers. Beam memory, it's just an optimization. I'm not sure, it just make it better, I guess. Sometime I tried it, but I didn't notice the difference. But maybe you can remove it. Drop last is when you have a batch size, assume you have 65 samples, okay? When the batch size is 32. The first batch will have how many samples? The second? Third? 1, okay? This sometimes make problems, okay? So here, when you say drop last, it's like it drops this one.
Has only 1.
Yeah, if it doesn't accumulate to 32, drop it. Right? Clear? Okay. So here we don't do that with the validation because we don't want to drop samples from validation. Because if you are dropping samples from validation, maybe each time you try rerun this code, it will drop random different sample. So it will the score will not be correct. ما أدري إذا makes sense.
Like,
It will not be
yes.
stable.
Yeah. So yeah, basically train loader, validation loader. We define the model. Oh, finally we saw the model. It turns out we have 9 classes. Okay, and we convert this to the GPU. We have added W as optimizer. Weight decay. If you remember the weight decay, it's just regularization. You put and it helps the model being better. You can remove this, and it's a helper parameter. You can try to do it. Okay. We have something scheduler called one cycle learner rate. It's actually cosine, but okay. If you remember, the scheduler is just goes reduce the learner rate. There's something called warm up, which actually increase the learner rate, they reduce the learner rate. Okay. There's actually called something called cycles. Actually, when you reduce the learner rate and go again up and come again, it's like you repeat the cosine. Yeah, cosine learner rate, cosine period. Okay. So here it's like he used only one cycle learner rate. How he figured out it works better than scheduler? Hyperparameter. You will try it. Okay. And a lot of settings. He passed the optimizer. What is the maximum learner rate you want to go into? You will start from something and you will go down, right? You will go back up to the same amount of learner rate. Okay. So you have to specify this initial learner rate. And this is here the maximum learner rate. Okay. And the epochs. Okay. Steps per epochs. How many, it depends on the batch size, how many steps we have in each epoch. PCT start, I don't understand this one. And strategy is the cosine. Final divide factor, I don't know. It's related to the formula they use, so I'm not sure. But yeah, this is a scheduler. We can easily pass it into the training epoch and right. Okay. We stopped here, right, in the training epoch. Let's go to the training epoch. If you remember, we entered this first and we came here, right? Let's go to the training epoch. Train epoch. Yeah, this one. Firstly, we put the model in the train. We have 2 losses. One is cross entropy and one is binary cross entropy. This actually match our intuition, right? We have something here called A and B is for automatic mixed precision. If you remember the mixed precision in the optimization I mentioned maybe in the first day, I told you that always use mixed precision. It always have the memory you want and double the speed. Okay, so you will find it used in everywhere. Class. So how to use it? You actually define it like this. Okay, and in the loop you put this. Okay, torch.automatic mixed precision autocast, I guess. And here you will put float 16. You can GPT it, class. But the components is this one. You define the scalar. You use this with, and you have here a slightly different backward sentence. You will put scalar.scale loss backward. You can just ask GPT to do it, easy. But know the syntax. Know there's something called automatic precision, and it will be done like this. Okay. So yeah, let's go to the next ones. Here it defines the losses. He wants to track several losses, so he defines some I don't know, some trackers he defined above. It's not that important. It's just to make it organized. Then let's go to train load. So you have the train loader, and he picks samples from the train loader. This is just تقدم but it just shows the progress bar. Okay, but it actually gets samples from train loader into train loader. It's like you can forget this sentence. To be honest, I thought I was explaining this one, but it's like he defined all this sentence as one sentence. Okay, then he used it here, but you can remove this one and just pick the train loader as usual and put it here, and we get the batch. The batch includes the X and Y, right? X and Y?
X and 2Y.
Yeah, X and 2 Ys, but exactly to know what it exactly returns, just return to the dataset class. It returns this, okay? It returns 4 things. Then X, Y, the second target, and the sequence ID. Yeah, okay? So it's important to, it is not necessary that it always return X and Y, okay? Sometimes it returns the X and mask. Sometimes I return several masks. Sometimes maybe in the object detection I return the boxes, and I don't know, you have several things. Yeah, okay? So ensure you understand what it exactly returns. Let's go back here. So a step is actually just used by enumerate. You understand enumerate, right? It just gives you a count, okay? But this is the main. Exactly, okay? So here, it just go to this batch, pick one of the X's, and pick one of the Y's, and pick one of the second Y. Okay, pop is just something you can pick sample. It's like go into the list and pick 0. Make sense?
Is it like that or is it different?
I think we are using here dictionary. It's syntax stuff. You can think by using the list and use it. Okay. But the point is, we are taking three parts of the components we use. We convert them to the device. We have the batch size. We use this for the automatic precision. We substitute this into the model finally. Okay. We got two predictions. If you remember, we returned them in the forward Z1 and Z2. Okay. And we calculate the loss for the first one, the loss for the first two. We combine losses. It turns out we can actually use more than one loss at the same time. Okay. If you remember, this is the first lecture. I mentioned several architectures, the maybe YOLO, and if you remember the variation autoencoder now, you see the KL, the Berners plus the MSE. So you can actually define several losses, okay? Some of them like this, and use this as a single loss, as unified loss. Yeah. So you optimize them together, okay? Do you remember this? Again, the combination. It's also from the first lecture on Sunday. I told you that if you are GPU poor, okay, and want to simulate the batch size, a bigger batch size, okay, you can just calculate the gradient and don't update the weight. Calculate the gradient, don't update the weight. Calculate the gradient, don't update the weight. Then sum these gradients and update only once. Remember that, right? So yeah, this is how you do it, okay? Instead of he accumulate them, then sum them. He pick it, and if I have, for example, I want to accumulate 3 times, I'll divide the first by 3, the second by 3, third by 3, then I'll update with this, update with this, update with this. Does it make sense? It's like math stuff, okay? It's like instead of S1 plus S2 plus S3 divided by 3, I do S1 over 3 plus S2 over 3 plus S3 over 3. Make sense? So yeah, it's like what he is doing here. You don't have to understand the syntax now, but make it intuitive for you. So he have several lists to track the losses. He just put them here. He used this for updating the calculating the gradients. It's different from what you know before because we are using automatic mix precision. I just have different syntax. Okay. We have something here called clip-grad. What is this? Clip gradient. Why do we use this? Exploding gradient. It's a big, so you want to clip it. Okay. So basically, he defines it here, but we don't know if he uses it or not. It depends on the value here. He put some limit. If he put, for example, 1, so don't allow any value of gradient greater than 1. Okay, he just clip it to 1. So it depends on the value here. And then it's here where the gradient accumulation happens. Just enter this condition if the gradient accumulation step has been satisfied. And you want 3 steps. So you will just calculate the gradients and you will not get into this in the first step. In the second one, you will calculate the gradient and you will not get into this loop in this condition. In the third one, you calculate the gradient, you will get here and you will update the weights. Yeah, it makes sense, right? But actually use the gradient accumulation when you need it. So I guess here he put the accumulation step to 1, so it's like we don't use it the accumulation. Okay. So this is the simple thing you know already. And here we have the scheduler.step. Is this a step scheduler or an epoch scheduler? Step? Yes, it's step. Obviously, this whole function called train one epoch. So yeah, it's inside. You have step. Okay. Okay, if it's a step, what does this tell you about the number of epochs? Yeah, they are low. Yeah, they are low. Okay. Maybe not. Actually, this is the intuition how you choose the scheduler. Okay. But mostly you will try both and check what works best. Okay. But yeah, this for logging. It just after each step bring this stuff, the epoch, the time elapsed, the loss, the first loss, the combined loss, the first loss, the second loss, the value of the gradient. Why do we need this?
To see if it's getting closer or not.
Not closer. What do you mean?
Like go into the minimum.
No. We talk about the value of the gradient. Yeah, exactly. This is how you will see if it's exploding or vanishing. Okay, that's why we bring the gradient here. Because when we train and see the gradient, if we see the value is very big, then we know we have to flip it. Okay? And the learner rate, why do we need the learner rate here? Yeah? The scheduler, yeah, to see the scheduler, okay? And it's useful just to track this thing, why it works, because it tells you later, maybe whenever the learner rate go below a certain threshold, for example, the model is like stop learning, okay? So you'll know that you have to update the scheduler to just stop at this limit and start from this limit, okay? So it's useful to update this stuff at the training, okay? So yeah, this is the format, it's just syntax, yani. So, valid epoch is the same, but we just remove the updates, okay? So now we understand the training epoch and validation epoch. Let's go to the. It's here. You just combine the predictions here. Getting up after each batch. Yeah. For this one, it calculate argmax, which give you the class. So we are not concerned about the probabilities, right? Here the ground truth. The label themselves. Why do you think he? What do we want the prediction, but why he actually gathered the labels? Yeah, formative evaluation, but it's correct answer, okay? But actually, when I started, I actually I didn't see why this happens here. Why not taking just labels from the data frame at the beginning? It's a good question, okay? But this makes your life easier, okay? Because you will have mostly mistakes about aligning the predictions with the ground truth. Why? Because you are using k-fold, right? And when you use k-fold, you use shuffle equal true. So it's like, it's not that the first, second, third, and fourth samples are for the fault one. No, maybe the first one is fault 5, second one is fault 3, okay? So you will suffer a lot from aligning them. You can, but it will cause you problems, okay? So here we also can gather the ground truth as well, so we can align them together. We make our life easier without the problems, okay? And just really return everything. So let's go to the tail loop. Everything easy, 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 easy. So here, the epoch loops have the training epoch, validation epoch, format for scoring. It's like it's get predictions from here. Okay, so it's just format related to the competition. They have wanted in a specific format. Okay, and score. So he has some function here called score, where he can calculate, actually give the solution, the prediction here. I think submission. Submission is the prediction he actually making, and solution is the ground truth. And he got the scores. Makes sense, right? And yeah, what else? He just start time, he just bring the results. If every score gets the best score, it's like if you got a better result, okay, always save the model. Okay, so maybe you are training for 50 ebook, and if maybe each ebook takes 20 minutes for training, okay? So you train for the first, second, third, fourth, connection disconnected. Okay, so you spend a lot of time, and it's get wasted. Sometimes you can save the checkpoint like this and continue the training, for example. Okay, it might be. Yeah, exactly. Okay, it's not trivial. You have to save the checkpoint, you have to save the optimizer, you have to save the scheduler, you have to save several things. And it can be GPT if you want, but you can. Okay, and that's very useful if the training take a lot of time. And actually, you can save this here, so you can use them for inference later. And here, maybe you can see the name of this notebook, WaveNet, Pytorch, only training. So it actually, there's another notebook for inference, okay? And that's what happens actually in real world generally. If you're testing the code we are dealing with by far, we train and inference the test or validation at the same notebook, right? But generally, you train, you save the models like this, you save the checkpoint, we call these checkpoints, okay? And you will put them in dataset or something, and use them in inference in test. Make sense? And especially in Kaggle, the test set might take several hours to infer, okay? So if the training itself takes several hours to train, and that takes several hours to infer, and they give you limitation. You have at most maybe 9 hours to do the inference. So it's like you are losing not 3 hours if you are, for example, using the train with the inference in the same mode. That's why separating them is better. Make sense? So yeah, we just save it here. We just save the prediction as CSV. And I think even the probability you are saving them, and that's the tail loop. Easy, easy, easy. In the last one, I guess just pick the folds. Notice how in each fold we are training for several epochs. Okay, so you can see now maybe the hierarchy, we have steps, right? Steps, we have epochs, we have folds. Yeah, in each fold we'll use maybe 30 epochs, for example. Okay, so yeah, we just pick all these things, concatenate them. Why? What do we concatenate? What do we concatenate here at all? What do you think? It's related to k-fold. This is related to k-fold, but what exactly? Why do we concatenate them? Why do we need this? Actually, these are the predictions of the validation. Okay, but why do we concatenate them like this? Try to run the loop in your head, and this for validation. Okay, we will define it empty and keep fill it. Okay, we'll fill it with the prediction of the 0 fold, first fold, second fold, third fold, and fourth fold. Why? If you want to vary them, why not just calculate the accuracy inside?
Is concatenate here is because each, like you said, each fold runs its own epoch.
Yeah.
So he wants to concatenate the epoch, the fold with the epoch that had been run on this fold.
Not exactly. If you remember from, I think on Monday when I was visited the long session, I told you in k-fold we have two ways calculating the accuracy. The first one is after finishing each fold, I just print the accuracy, right? The second one, I told you can, not average, collect the predictions, okay? Collect the prediction of the first fold, keep it, don't calculate accuracy. The second fold, concatenate it, don't calculate accuracy. Third, fourth, fifth. So we have predictions for the whole data set. So we only calculate the accuracy only once with the full predictions with the full data. Make sense? Actually, this has some benefits and it usually gives better results, but that's what we do here. So after it's all finished, and you can see how it goes. For example, remain time, loss, loss, loss. The gradient here is values 4. The linear rate, you can notice how it decreases. Okay. Yes, and looks the gradient is good. So I assume he don't apply any max, gradient clipping, for example. Okay. Until the end. Wow, it's too long. Yeah. Okay. Yeah, we have the score 66 for the first binary, 94 for the second one, 30. Easy, right? Easy. But there's, if you notice now, we almost cover everything with it, a notebook, okay? But maybe only this one, we missed configuration. If you notice, maybe we have to look at the schedule, for example, or this stuff. Look here. For example, here, he defined gradient accumulation steps, okay? He said that you will find them in the config. Okay? The linear rate, where is the scheduler defined? I'm not sure. Anyway, each one is defined and we have config where you put all the settings, okay? That's actually maybe a good practice. We have the configuration here. Do you want to apply the automatic mix precision? He said false, don't use it. By side of train, by side of validation, whether it is debugging or not. So if it's debugging, use 2 epochs. If not, debugging just use maybe 10 samples, for example, and maybe 2 epochs, for example, just to ensure that code works. Then, if it works end to end, okay, run the whole data, because maybe the whole data takes 6 hours, and you don't want to run 6 hours, and it tells you pandas not defined. Yeah, but yeah, we have 30 epochs, we have 5 folds. This accumulation step is 1, so it's like he are not accumulating steps. Okay, then rate 1e negative 3. Max grad norm 1e7, so it's like 10 millions. It tells you that he is not clipping gradients. So it's like it's almost free. Okay, use whatever gradient you want. But you can, for example, put it 1 to clip them to 1. Okay. Number of workers 0. I think it means no multi-processing, but I guess you should increase this to 2 or something, depends on your processor.
No, I think it's used a bit for your local computer.
From what I remember, I guess if you put -1, it will use all the cores. Okay. If you put 0, it will stop the multiprocessing and maybe use only once. If you put specific number, it will use this number of cores. I guess that's what I'm understanding.
Maybe. I think Abdul Hamad said that in stage 3. He thought number 4 at 0, it would work with the best for you. I think you thought about another similar function.
Maybe. Okay, نتعلم يعني كل يوم. We have range frequency. It means that if you remember in the prediction in the result, the end result here, it's like notice he is printing after each 20 steps. Okay, to not make the logs too much. So yeah, train full data equal false. Actually, here he is using train and validation on the validation result, right? So if you want to submit to the leaderboard later, he will pick these checkpoints he got, he infer the test and make prediction for the test and use it for submission, right? But after you validate your model, tune all parameters, sometimes it might give you a boost in the score if you trained on the full data instead of 80%, 80%, 80%. No, train on full data and make prediction on the test directly. But if you trained on the full data, you cannot see the validation score. So you firstly start with k-fold, check the score, tune all the parameters until you already reach the best score, then train on the full data. Makes sense, right? Yeah. If you remember from the session, we said usually you can start by early stopping, put 1000 ebook and use early stopping, okay? It might don't tell you the range, maybe 30, 40, okay? In cross, but it doesn't matter with regardless of the. Actually, this is a really interesting point. Yani, we have five faults, so we train the models five times, right? So maybe if I use early stopping, the first fault might give you 30 ebook. The second might give you 70 ebook. Okay, the third maybe 20 ebook. How should I encounter this? Okay. You have two options. Firstly, is just use early stopping as is, keep it, okay, and just pick the option it gives you. Okay. I start by this at the beginning, but as I go, I try to fix the number of it. Maybe I try to average, like if the first one give the best result at 30, the second at 60, the maybe next one at 20, for example. I try to get an average and pick that ebook and just use a scheduler on it. Okay, but yeah, easier to just use this if you want. Yeah, you can use that as an estimate, I guess. Okay. And have like decay as the one we used down. So easy. Any problems? Sorry? Yeah, for the randomness, yeah. Have you heard about seed 42? Why people put random state equal 42? What do you think? Okay. Actually, let me give you exactly the answer. It's actually it's related to some, I guess, episodes of an old series or something. It's like someone in I don't know, in some fiction actually asked the computer what is the ultimate question of life, the universe, and living, and the computer said 42. So we would just keep using 42, but it's up to you. You can use any number of seeds, Okay.
I think this one is zero for most cases.
No, that doesn't. It's really random. You can try that, but even tuning the seed might be sort of fitting. Sometimes we actually train the model on one seed, but at the end of the competition, we use maybe 50 seeds, train the model 50 times, average all these predictions to stabilize it more. But no, there's not a seed that's better than another one. Okay. Easy. Yeah. Any problems with this one? Any problems? Please ask. If you just literally copy and edit, just submit to the notebook, you already will be in the leaderboard of this nice competition. So it might be your start if you want, just finish after I think two months or something. So yeah, have fun. Actually, I plan to cover another one, but I think this already went too long, and that one is actually significantly harder, I guess. No, it must be easier. Maybe next time. Okay, next week, inshallah. Actually, I planned for this one. As I mentioned here, is to understand how to understand a bit of a complex Pytorch code. I will go through another code maybe in the next week. Okay, I'll go through EDA. Really interested in this one. In that one I'll just start reading from here. Okay, and get into the data and keep reading all the discussion and try to brainstorm ideas here. Yeah. Okay, so maybe you can brainstorm ideas with me. I'll tell you some ideas I have. I think this will be very useful for how to formulate the problems. And this is a real world problem. They give you some domain knowledge about what the data contains and what's the task you have here. Okay, and you should build AI. How would you use that? What's the best model? You see that we use 1D CNN, right? Here, the wave nature is 1D CNN. There is the transformer, there is the STM. You can actually even consider this problem as a tabular problem, and you can use KAUST and XGBoost, and so you can see different perspectives. Okay, so I think such discussion will be very useful. So maybe next week, inshallah.